Why is it so dang hard to shoot these freaking falcons? Finally. How do bows work? Hello, Count Sacke here, back with another Genshin Impact video. Today, I'll be discussing the physics of the charged bowshot. To be more specific, I'll determine an equation to predict the motion of the arrow. While we're at it, we'll also take the time to see if the gravitational acceleration of arrows is the same as the player's. This video was created due to a poll that I held months ago. I'd like to thank everyone who responded. Don't forget to leave a like on the video, and subscribe so you'll remember me even if the YouTube algorithm decides to hide me forever. Lastly, if you haven't watched my video series about Genshin's gravity, there are concepts that I will be using here, so I would highly recommend that you watch it. I'll try to explain the essentials, but I won't be as in-depth. With that, let's get started. When I first fired a charged shot with Amber back when the game was released, I remember feeling that the arrow accuracy was quite high. I expected to have to aim a lot higher above the target than you actually do in-game. When closer to a target, you actually want to aim more directly at the target. Even to this day, I sometimes aim just a bit too high. Of course, when you move really far out, you actually need to start properly arcing your shots in order to land a hit. It wasn't until I started creating this video that I realized why. When you take a shot, the arrow actually moves in a completely straight line along the direction you are aiming. It is because of this that charged shots do align very well when the target is close to the player. Hence, why arrow accuracy felt so high to me. It is only after some time that the arrow begins to dip down towards the ground. Another thing to note is that each character aims in a circular arc around the player. This means that the initial height and horizontal distance that an arrow is fired changes depending on the vertical angle. The horizontal angle doesn't really change much in the grand scheme of things. The reality is that, even though we're dealing with 3D space, we can actually only treat it as a 2D system, since it's possible to define the coordinates in such a way that the arrow only moves along two axes. We'll let the x-axis be along the direction that the player aims in, and the y-axis will be the height. The reason this works is because the arrow moves directly forward. If the arrow was to veer off to the left or the right, then we would have no choice but to use 3D. Apparently, Chlorine still needs to account for wind to snipe even though our arrows don't.
Calculate distance. Correct for wind speed and humidity. Ready.
Well, lucky us, I guess. Lastly, it actually doesn't matter if you do a full charge shot or if you just fire while aiming. If you don't believe me, here's a clip with a fully charged shot, and here's one that's not even charged up at all. They follow the same exact trajectory. Before we create the model, it is best that we take some time to review projectile motion. To quickly recap, a projectile is any object only experiencing the gravitational force. As a byproduct of gravity being the only force it experiences, projectiles have constant acceleration. This means that we can apply the kinematic equations to them. It's important to remember that gravity only affects the vertical motion of an object, so the horizontal motion is independent from it. This means projectiles move at a constant horizontal velocity, while their vertical velocity changes. Because these equations make use of vectors, we can focus on the vertical and horizontal components individually. Vertically, it is affected by gravity, so it experiences downward acceleration. But the horizontal component doesn't accelerate, as stated earlier, so it moves forward at a constant velocity. In the previous videos, I've only focused on the vertical component. However, when dealing with bows and arrows, we also need to consider the horizontal component. The arrows can be approximated as a projectile thrown at an angle. Thrown projectiles are modeled by assuming that, at the moment the object is launched, it receives an initial velocity. This velocity embodies the direction the object was thrown through its vertical angle, and the strength of the throw is based on the magnitude of the initial velocity. Because velocity is a vector, we can split up the initial velocity into two vectors, one vertical and one horizontal, using trigonometry. Splitting up this velocity into its horizontal and vertical components allows us to use the kinematic equations shown earlier, and that's all that's needed to fully model the motions of arrows in Genshin Impact. Alright, let's back up a little. When the arrow is fired, it moves in a perfectly straight line. This tells me that the arrow is moving with a constant velocity and can't be affected by gravity. However, after a brief period of time, the arrow's path starts to curve and it begins to fall. This curving motion means that it is now accelerating downward. Here, we can see that there are two parts to the arrow's motion. In the first part, velocity is constant, and in the second part, the arrow experiences a downward acceleration, which is where we can apply projectile motion. To be able to fully model the movement of arrows, there are three things that we need: the angle that the arrow was shot from, theta, how fast the arrow was initially traveling upon shooting it, vi, and how long the arrow travels at constant velocity, ta. As mentioned earlier, as soon as the arrow is shot, it receives an initial velocity, vi, which can be split up into its horizontal and vertical components using trigonometry. We have that the initial vertical velocity, or viy, is equal to vi times sine theta. And then for the initial horizontal velocity, vix, that is equal to vx, which is also equal to vi cosine theta. For the horizontal and vertical motion during the constant velocity portion, we can make use of the kinematic equations assuming that the acceleration is equal to 0 to retrieve equations for the horizontal and vertical positions. Starting with the horizontal component, we can see that the acceleration, or a1x, is equal to 0. This means that v1x is equal to vix. Then, for the horizontal position, we find that x1 is equal to vixt plus xi. For the vertical component, a1y is also equal to 0 in this portion. So, we see that v1y is equal to viy. Then, for the position, we get that y1 is equal to viy times t plus yi. These equations are valid as long as t is less than ta. After ta, the arrow experiences a downward acceleration due to gravity. Here, we can make use of the equations for projectile motion in this situation. For the horizontal component, the acceleration is still 0, so ax is equal to 0. This means that v2x is equal to v2ix. Then for the position, it's x2 is equal to v2ix times the quantity t minus ta plus x2i. On the vertical component, we have that ay is equal to negative g. The minus is because of the downward direction. For the vertical velocity, v2y is equal to negative g times the quantity t minus ta plus v2iy. Then for the position, we get y2 is equal to negative g times the quantity t minus ta squared divided by 2 plus v2iy times the quantity t minus ta plus y2i. Notice that instead of just t, there are t minus ta. The reason why is because t is measured from 0 seconds. However, the arrow only starts to accelerate after ta. If you just put t, it would be as if the arrow started falling down immediately, which doesn't happen. It only happens after ta amount of seconds, hence t minus ta. The equations are relatively simple enough. However, we also need to make sure that these two models continuously mesh with each other. If we're not careful, the model could predict that the arrow would teleport from one height to another at ta. Another possible problem is that it might predict a sudden instantaneous change in the object's velocity for no reason. Take for example a car. You wouldn't expect it to suddenly just teleport a few meters forward or backward, and you would also not expect it to go from 0 kilometers per hour to 40 kilometers per hour literally instantly. What we need to do is to make sure that they predict the same position and the same velocity at the moment the arrow starts accelerating for both the horizontal and vertical components. In short, the following conditions must be met. v1x of ta is equal to v2x at ta, then v1y ta is equal to v2y ta, x1 ta is equal to x2 ta, and y1 ta is equal to y2 ta. Let's start with the velocities. v1x at ta is equal to v2x at ta. Well, this one's quite simple since it's just literally vix is equal to v2ix. For v1y is equal to v2y at time is equal to ta, we see that viy is equal to negative g ta minus ta plus 2iy. The ta minus ta, it goes to 0, and hence we get that viy is equal to v2iy. From this, we find that whatever the initial velocity is when the arrow was shot, that is the initial velocity for when it starts to curve or when it starts to accelerate. This should make sense because the velocity remains constant. Now for the horizontal position, x1 is equal to x2 at time is equal to ta. So we can substitute for x1 and x2, which gives us vix times ta plus xi is equal to vix times ta minus ta plus x2i. The ta minus ta cancels out to 0, so we're left with x2i is equal to vix times ta plus xi. Now if we plug x2i back into the equation for x2, it becomes x2 is equal to vix times t minus ta plus vix ta plus xi. Then we can distribute the vix into the parentheses, and then we can notice that vix times ta is cancelled out, resulting in x2 is equal to vix plus xi. Notice that this expression is exactly the same as x1. The reason why is because the horizontal velocity of the object doesn't experience any acceleration, so naturally, the equation for horizontal position should be the same. Now for the vertical position. We start off with y1 is equal to y2 at time is equal to ta. Substituting for y1 and y2, we get viy times ta plus yi is equal to minus g times ta minus ta squared divided by 2 plus viy ta minus ta plus y2i. The ta minus ta's cancel out to 0, And we're left with y2i is equal to viy times ta plus yi. Earlier I mentioned that the initial position for the arrow changes depending on the vertical angle. To be able to determine xi and yi, recall that the characters aim the bow along a circular arc. This implies we have to use some trigonometry. Let the radius of the circular arc be r arm. What I'll do is define yp as the height that an arrow is fired when theta is equal to 0, relative to the ground the player is standing on. And y0 is the height of the ground the player is standing on. This means that xi is equal to r arm times cosine theta, and yi is equal to yp plus r arm times sine theta plus y0. These are the equations that we have to fully model the trajectory of arrows. For the positions, x is equal to vix times t plus xi. Then for y, it is equal to viy times t plus yi, provided that t is greater than or equal to 0 but less than ta. However, when t is greater than or equal to ta, y is equal to minus g times t minus ta squared divided by 2 plus viy times t plus yi. For the initial velocities, vix is equal to vi times cosine theta, and viy is equal to vi times sine theta. Lastly, for the initial horizontal and vertical positions, xi is equal to r arm times cosine theta, and yi is equal to yp plus r arm times sine theta plus y0. Now that we have our equations, we just need to measure the 5 constants: vi, g, ta, yp, and r arm. So how do we do that? The first thing to note is that out of all of the variables that are in these equations, the only one that the player can control is the vertical angle theta. All other parameters are out of our control. The easiest to measure out of all of them is yp. We just have to use height measurements, which can be done by varying the height of a platform and taking note of its height. Let's now focus on vi and r arm. This one honestly took me the longest to figure out, especially r arm. Notice that if theta is equal to 0 degrees, the horizontal velocity becomes equal to the initial velocity. If theta is equal to 90 degrees on the other hand, the vertical velocity becomes equal to the initial velocity. Now, the reason why this is the case is because cosine of 0 degrees is equal to 1, and then sine of 90 degrees is equal to 1. In Genshin, we cannot aim directly upwards, but we certainly can aim horizontally. This means that so long as we aim parallel to the ground, we should be able to measure the initial arrow speed. However, we also need the horizontal displacement. We can measure the horizontal distance by using the leisure device Twang Bang Bang minigame in the teapot. In this minigame, the distance from the player to the explosive barrel is shown. This implies that the equation for the distance is the following: d is equal to delta r plus r arm, where delta r is the distance that the arrow actually travels, which is equal to vi times t. Note that in this experiment, we'll be aiming parallel to the ground, so vi does equal to vix. Substituting for delta r, we get that d is equal to vi times t plus r arm. Notice that the equation for the distance shown on the barrel should be a straight line. The d looks like a y, the vi is the slope, x is the t, and our arm is b. So essentially, we can collect a bunch of data points with the time it takes for the arrow to reach the barrel for all of the distances considered. From here, all we need to do is solve for a value of vi and our arm that predicts d with the least possible error, which can be done by using linear regression. If you don't know about linear regression, you can watch these videos where I go more in depth about curve fitting. Using the equations for the matrix form of linear regression, or specifically multiple linear regression, we can arrive at an equation that predicts the most optimal values for the slope and the y-intercept such that the error is minimized. In the end, these are the equations we can use to solve for our arm and vi. Now, how do we determine the time that it takes for the arrow to start accelerating downward, or TA? What we have to do is recall the arrow position equation from earlier. If we consider a case where the arrow travels for longer than TA, we have this equation for the arrow height. Y is equal to negative g times t minus ta squared divided by 2 plus viy times t plus yi. We can measure the time it takes for the arrow to hit the ground. So after t amount of seconds, y is equal to 0 since we define the ground to have a y position of 0. Next, we have to consider that if we aim horizontally, theta is equal to 0 degrees. This implies that VIY is also equal to 0 because sine of 0 degrees is equal to 0, and VI times 0 is 0. In addition, it also implies that YI becomes equal to YP plus Y naught. After doing a bit of algebra, we end up with two possible solutions for TA. TA is equal to t minus plus the square root of 2yi divided by g. Now recall that t must be greater than or equal to ta, so therefore the only valid solution for ta must be the one with the minus sign, otherwise ta would be greater than t. So therefore ta is equal to t minus the square root of 2yi divided by g. There's just one last issue. We don't know if the arrow's gravitational acceleration is 20.4 meters per second squared. That might only be applicable to the player. To solve this, what we can do is fire arrows at different heights. Because TA should be the same, we can do some algebra and calculate an expression for g. So we have that TA is equal to t1 minus the square root of 2 times yi1 divided by g, and that is also equal to t2 minus the square root of 2 times yi2 divided by g. After going through more algebra, we eventually arrive at the solution that g is equal to 2 times the quantity the square root of yi2 minus the square root of yi1 divided by t2 minus t1, all of that squared. Coming up with the experiments for this was particularly difficult for me to do. I had to go through multiple different ideas for how to measure our arm. Another difficult aspect is the angle of the bow shot. We don't really have any references for angles. I would like to try to keep the player's charge shots aimed parallel to the ground, but I can't guarantee that it is. I was hoping that the reset aim would do this, but nope. It actually points you downward a little bit. Regardless, there are 3 experiments that we need to perform. First is for measuring the initial height that an arrow is fired at when aiming horizontally, YP. Second is for measuring the downward gravitational acceleration of the arrow, G, and the time it takes for the arrow to start being accelerated, TA. Third is for measuring both the radial distance the arrow is fired at, our arm, and the initial velocity of the arrow, VI. For all of the experiments, we'll be performing them in the Serenity Pot. In addition, they will all be using floating platforms. I specifically used the Subspace Structures Suspended Pathway. You'll need a lot of these platforms if you don't want to do a lot of editing, so I would recommend maybe 20 to 30, so if you want to do these on your own. Regardless, I had a lot of them. Experiment 3 will be making use of the Leisure Device Twang Bang Bang minigame. This can be purchased from Tubby. Last, we need to perform these experiments for all of the different character models. On screen is a list of all the different bow characters organized based on their model as of version 5.1. The characters I've chosen are Kujo-Sara, Kale, Diona, and Goro. Unfortunately, I don't have Child, and he's the only tall male character with a bow. Anyway, to help with aiming more accurately, I would recommend lowering the vertical and horizontal camera sensitivity to the lowest value. Starting with experiment 1, we first need to create the setup. For each character, we'll have 2 platforms. One is placed 1 meter off the ground. This is where the player will stand on, and I'll call it the step platform. The second platform will be involved in the procedure, which I'll call the reference platform. So here are the steps for the experiment. First, place the reference platform 0.5 meters above the step platform. Make sure to leave space for the player to stand on the step platform. Note, the player should not be on top of the reference platform. 2. Aim with a charged shot and move the player such that they are touching the reference platform. Third, aim in the direction of the reference platform straight forward, parallel to the ground, and fire an arrow. If the arrow didn't immediately hit the reference platform, proceed to step 4. If the arrow hits the upper platform, lower the height of the upper platform by 0.1 meters until it can no longer hit it, and record the height of the reference platform. The height of the reference platform is YP for that specific character model. For step 4, which is if the arrow did not hit the reference platform, raise the reference platform by 0.1 meters, and then for step 5, repeat from step 2. Note that the height of the platforms is indicated at the top left of the screen in the editor when selecting the reference platform. The goal is to find the minimum height that the arrow is fired at, YP. So YP would be the maximum height an arrow can pass above the top side of the reference platform without hitting it. To aid in aiming more accurately with an angle of 0 degrees, I placed another platform called the 0 degree platform far in the distance in front at the same height as the reference platform. It needs to be far away to take into account field of view and perspective. If it's far away, these effects roughly cancel out. I would personally recommend that you set the time to day because the platforms can be a little difficult to see at night. In Experiment 2, we'll be expanding upon the apparatus in Experiment 1. The procedure is as follows. Place another step, reference, and 0-degree platform at a taller height than that in Experiment 1. I chose the second step to be at a height at 12 meters, but you could technically choose any height. Second, at the lower step platform, aim with a charged shot parallel to the ground using the 0-degree platform as reference. Third, fire a charged shot and measure the time it takes for the arrow to hit the ground. 4. Repeat from step 2 but at the second step platform, which is higher above. 5th, calculate G and TA with the following formulas. Note that for these equations, the variables with a subscript of 1 are at a lower height, so T2 must be greater than T1, and yi2 must be greater than yi1. We can then just take the averages to find approximations of their values. For Experiment 3, we'll be using the Leisure Device Twang Bang Bang minigame and creating a different setup. In the editor, place down a long platform as shown on screen. At the end of the platform, place an explosive barrel 1 meter below the platform and halfway under the edge like this. Lastly, place another platform 0.1 meters above the character model's YP that was measured in Experiment 1. For the procedure, 1. Stand on the long platform and aim above the barrel with a charged shot parallel to the ground. Use the 0-degree platform as reference. The crosshair should be aligned with it. 2. Move the player to a distance of 2 meters in front of the explosive barrel. 3. Fire a charge shot, or multiple, and measure the time it takes to hit the wall. 4. Move back 1 meter and repeat step 3 until the distance indicates 21 meters. 5. Using the following equations, calculate R-arm and VI. I want to point out that the distance shown above the explosive barrel has no decimal points, so the distance displayed is only reliable at the moment the number changes. I double-checked to make sure that the distance wasn't rounded up or down, like, for example, if it was actually 5.5 meters but 6 meters was displayed. Well, turns out at the moment the number changes, the distance shown is rounded. You have to keep in mind if you're going towards or away from the barrel. For example, if the distance goes from 1 to 2, you would know that you're at 1.5 meters away. Whereas, if it goes from 3 to 2, you will be at 2.5 meters. One more thing before we head to the results. All these experiments should be repeated for each character model. The reason why is because we don't actually know if there are differences between them, so whatever the case, if there are similar values, we can then be confident and say, hey, they have the same value. From the Experiment 1 results, these are the initial heights, YP, for each of the character models. Something I did find a little interesting is that the medium male models have a shorter YP than the medium female models. My guess as to why this is the case is because of the way the medium male characters hold their bows. Notice that Goro is holding the bow horizontally, while Kale holds it upright. For Experiment 2, these are the arrow gravitational accelerations G and the time it takes for the arrows to start accelerating TA, arranged based on the character model. Notice that all of the character models have G and TA values relatively close to each other. This implies that it is very likely that all models share the same G and TA. On the bottom of the table, we can see that the overall average of the arrow gravitational acceleration is 5.345 meters per second squared, with a standard deviation of 0.174. Meanwhile, for the time taken to start accelerating, the overall average is about 0.525 seconds, with a standard deviation of 0.33. Lastly, this table shows the summary of results from Experiment 3. It shows the initial velocities of the arrows, vi, and the radius of the circular arc that the player aims horizontally along, r-arm. For the uncertainties, I used a confidence level of 95%. This basically means that the probability that the true value is within the interval is about 95%. I went with the standard alpha is equal to 5% because I didn't really have any expectations for what the level of significance should be. The first thing that catches my eye is that, well, our arm appears to be negative. Wait, that doesn't make any sense. Okay, I might have an idea as to why our arm is negative. Actually, two. It could be because of the way I measured the time or the way I measured the distance. I specifically measure time from the first frame that the character's arm moves to the first frame that the hit effect of the arrow on the platform is shown. For distance, I measured it based on the value displayed above the explosive barrel. I did measure if the distance shown was rounded, but when I think about it, I used speeds of the players that I measured back in my measuring distances video. However, I think I can still improve the accuracy of the measured speeds. With the data that we currently have, we'll just have to say that our arm is negative. It's also worth pointing out that the standard error for our arm, SE our arm hat, is at least 5.5, and that is a very large number. This large value in the standard error is why the 95% confidence interval is so large, with the medium female model having the largest uncertainty, where our arm ranges from negative 15.512 to positive 12.252. Clearly, our arm is not very precise. When looking at the standard errors for VI, SE of VI hat, they don't even reach a value of 2. It's not large, but it's technically not that small either. However, in comparison with the standard error seen in our arm, the uncertainty is certainly a lot smaller for VI. I want to point out that despite our arm not making much sense, VI should actually not be affected by this. The reason is because the initial velocity of the arrow is only really dependent on the slope that the plot points have. In other words, VI only depends on the relative distance between each data point. If all time and/or distance measurements are shifted by the same amount, the slope will remain the same. Think about it. You can move a line up, down, left, or right without necessarily changing its slope. Even then, based on our data, we can see that the initial velocities are actually very consistent regardless of the character model. This can be seen with this time versus distance plot. Observe that the slope of the lines are practically equal. Note that this considers the averages of the measured times per distance. I personally hypothesized that the initial velocity is actually 50 meters per second. With that assumption, while keeping our arm the same, the r squared actually remains relatively the same too. This implies that even with the initial velocity being 50 meters per second, it is still able to very accurately predict the data. With that, I think this covers most of everything that I can do for now. In conclusion, I derived a set of equations that can model charged bow shots in Genshin Impact and measure the parameters YP, VI, R arm, G, and TA. Their values are shown on screen. For our arm, the values were negative, which doesn't make much sense. This does mean that we cannot reliably say what the values for our arm should be. Fortunately, this result doesn't affect the validity of VI. We can also conclude that the arrow's gravitational acceleration is different from the player's gravitational acceleration by quite a large margin. For recommendations, I would like to ask those who own Tartaglia to measure the tall male model bow character's charge shot constants, as I don't have him, and I don't really plan on getting him anytime in the near future at all. Sorry, child mains. This video has all the details you need to be able to perform the experiments yourself. This is why I go at lengths to describe the process and how I actually do these experiments and whatnot, and all the equations, the derivations, and whatever. It's so that you understand where everything is coming from, and that I'm not just pulling these numbers out of my ass. Second, for our arm, I unfortunately don't have a good way to determine its value. I have thought about continuously firing arrows at a wall and then checking the distance it starts hitting the wall instantly, but the problem with this is that measuring the distance could be very difficult. If you have any ideas, I would love to hear them. Third, experiments need to be conducted to verify the accuracy of the model I've deployed. I have a few ideas for how to accomplish this, but those will have to wait for another video. It's a little late for a disclaimer, but just because you know the physics of how the arrows work doesn't mean you'll suddenly become a bowshot god. That is evident by the fact that people can become amazing at sniping despite not knowing a single thing that I talked about in this video. Aiming is a skill that you need to develop on your own. Knowing the physics behind it just helps make quantitative predictions. If you haven't already, be sure to like and subscribe. If you guys could share the video, I would greatly appreciate it if you could. I really only expect 30 to 50 views at most. I also would like to apologize to all of my new subscribers, all of the recent members who've discovered me over the past few videos I've uploaded. This video took longer to upload than the previous ones, I very much admit that. I was very busy with IRL stuff over the last few months, and making the experiments for this one was very difficult. I literally had to simulate the experiments in a spreadsheet just to make sure that they made sense. If it already wasn't enough, Experiment 3 had 400 samples, and measuring the times in my video editor took hours. Anyway, I thank those who maintain their patience with me. Thanks for watching, and hope you've enjoyed.